In this video, we are going to talk about connected components and how we can find connected components using depth-first search. So the connected component of an undirected graph is a subgraph in which each pair of nodes is connected by a path. And this subgraph is not connected to any additional vertices in the rest of the graph. Now there can be more than one connected component for a given graph, and the intersection between these different connected components would be a null set. That means these connected component sets will be pairwise disjoint. Also, the union of the connected components will give the set of all vertices of a given graph. Let's take example. So if this is the given graph G with this set of vertices, we can see that all these vertices are connected to each other. There is a path between each and every pair of nodes. So there is a path between A and B, A and C, A and D, A and E, A and F. Similarly with B, with all other nodes, and similarly with other vertices of the graph, there is a path which is connecting each and every pair of vertices. So we can say that there is only one connected component, and this connected component is a set of all the vertices of the graph. Now consider this again another graph. If you look at this graph, we can see that this set of vertices A, B, E and F, they are connected to each other, but they are not connected to any other vertex outside of this. Another subgraph we see is with this two pairs of nodes, this pair of nodes, and again they are connected to each other but not connected to any other vertex. So we can say that there are two connected components, C1 consisting of A, B, E and F, and C2 consisting of C and D. So there are two connected components. Each node of C1 is connected to other nodes of C1 but not connected to any other node outside of C1. Similarly with C2. Also, the intersection of C1 and C2 is a null set, but their union will give us the complete set of vertices. This is another graph. We see that this is one connected component, this is one connected component, and this is another connected component. So these are the three connected components. These are subgraphs of the original graph. Each subgraph is, let's say, C1. The nodes in this connected component are connected to each other but not connected to any other vertex outside of this. Similarly, C and D of C2 are connected to each other but not connected to any other node. Similarly for C3, F is an isolated node not connected with other nodes of the graph. So what are the applications of connected components? In graph theory, of course, it can be used to find subgraphs or clusters of nodes connected to each other. In computer networks, it can be used to discover cluster of nodes or devices that are linked and have similar qualities like same bandwidth. In image processing, they can be used to find connected pixels having similar characteristics, like for example, pixels connected to each other having the same intensity. So now we'll take a look at a pseudocode of finding connected components using depth-first search. So this is the pseudocode. This is the main function, which is the connected components, where the input is the graph with a set of vertices V and a set of edges E. Within this main function, we are going to initialize the variable count to 0. This count is going to give us the number of connected components in G. We have an array visited. The size of this array is equal to the number of vertices in the graph. So if the number of the vertices in the graph is equal to n, then the size of this array is n elements. Now for all the vertices in the graph, we are going to initialize this visited array to false. So each element of this array has been initialized to false. For all the vertices in V, Now we are going to check whether the vertex has been visited or not. So only if the vertex is unvisited, we are going to call a depth first search for that particular vertex and increment the count by 1. Once we have done this for all the unvisited vertices, we are going to print the count. Now this depth first search pseudocode, you would have learnt this algorithm earlier. If for details you can check my depth first search video posted earlier. Whenever we call depth first search for a node, for that node we are going to mark it as visited, and now we are going to check the neighborhood of that vertex. So for checking the neighborhood, we will have to check the adjacency list of that vertex, and in all the neighborhood we are going to find the unvisited neighbors. That means visited should be false. If the neighbor is unvisited, we are going to recursively call DFS for that vertex. So let's take an example and see how it works. So this is our given graph, and it has a set of vertices A, B, C, D, E, F, G. We have initialized a visited array to false for each of the vertex, and our initial count is 0. So we are going to call this function connected components. We are going to randomly select a node. So let's say we have selected A. So we are going to call DFS on A, and whenever in connected components we call the DFS, in the main function when we call DFS, we are going to increment the count. So the count has gone from 0 to 1. Now when we call DFS on A, we are going to mark A as visited. So A has been marked as visited, and we are now going to explore the neighborhood of A. So we see that there are 2 unvisited neighbors of A, B and E. So we have to go and recursively call DFS on these unvisited neighbors. So let's say we randomly select B. So we will now call DFS on B. When we call DFS on B, we will mark B as visited. So B has also been marked as visited, and now we will check neighborhood of B. So there are 2 unvisited neighbors, E and G. So let's say we select E, and so we are going to call DFS on E now. So we call DFS in E, so we mark E also as visited, and we will check unvisited neighbors of E. There are 2 neighbors of E, A and B, but both are visited. So now we have to backtrack to B. So we backtrack to B and explore other unvisited neighbors of B. So there is one which is G. So we go to G and call a DFS on G. So when we call DFS on G, we will mark D also as visited. Now we check the unvisited neighbors of G. There are none. So we backtrack to B. There are no other unvisited neighbors of B. So we backtrack to A. Again, we see that there are no unvisited neighbors of A. So we go back, return back to our main algorithm of connected components. Now the main algorithm, after it has returned from DFS of A, now it will check which are the other unvisited nodes of the graph. Now we can take F, which is an unvisited node of the graph. So we can call DFS, and now because we are calling DFS from the main algorithm, we can increment the count to 2. So we call DFS on F, so we mark it as visited. So F has been marked as visited now. We check the neighborhood of F, so there is none. So we have to return back to our main calling function, which was the connected components. So we go back to that algorithm. So now in this main function, we see what are the other unvisited nodes of the graph. So C and D are unvisited. So we can pick either of them. Let's say we pick C. So now we will go call DFS on C, and because we are calling it from the main function, we are going to increment the count to 3. So when we call DFS on C, we will mark C as visited, and check the neighborhood of C for unvisited neighbors. There is one unvisited neighbor which is D. So now we have to call DFS on D. So we call DFS on D and mark it as true. Now we check more unvisited neighbors of D. There are none. So we have to backtrack to C. We check more unvisited neighbors of C. There are none. So that means we have to return to our main connected components function. When we go back to the main function and we now see what are the other unvisited neighbors of unvisited vertices of the graph, we can see that all the vertices have been visited. So there are no other vertices left and our final count is 3. So we have found these 3 connected components C1, C2 and C3. We can see that within each component the nodes are connected to each other, but they are not connected to any node outside of that component. No node of C1 is connected to nodes in C2 and C3. No node in C2 is connected to nodes in C1 and C3. And similarly for nodes in C3. We also see that the intersection of these 3 components is a null set, and the union is going to give us the set of all vertices in the graph. If we want, we can get the nodes of the components also printed while we are calling DFS. So this is how we can find the number of connected components using depth first search.